Welcome back to Basic Biostatistics 2, and this is session 8, Multiple Linear Regression. In this session, I would like you to understand how to run multiple linear regression models, how to select the most efficient and how the most complete model using F values and R square values. I would also like you to get familiar in interpreting the findings of the results of the SPSS analysis and to see how to control for other variables in multiple linear regression models. Multiple linear regression models are similar like linear regression models, but with the difference that it has more than one independent variables. Thus, the assumption of the models are the same. The outcome variable, or dependent variable, as it also called sometimes, has to be continuous and normally distributed. The independent variable, or the exposure variable, has to be normally distributed as well in case if it's a continuous variable. You can add categorical variables as well to the multiple linear regression model. However, if the variable is categorical, it has to be dichotomous, meaning only having two categories, yes or no, for instance, or smoking and non-smoking. Good, so far so good. Let us see how linear regression model or multiple linear regression model works in a specific example. Let's try to assess whether the fruit and vegetable consumption predicts BMI in our dwarfs. Using the fruits and vegetable consumption variable as a continuous variable, it's normally distributed as we know from session 2, and BMI as a continuous variable. In addition, I would like to add age as a continuous variable to the model in order to know whether if we adjust the results for age, whether the fruit and vegetable association is still valid in our statistical model. I go to analyze, we go down all the way down to regression model, and as we did before in session 7, we go to linear regression. Now we define that our outcome or dependent variable is BMI. We select BMI from the window on the left where we have all variables and move it to the dependent variable window. Now I would like to know fruit and vegetable intake, whether this is associated with our dependent variables. The fruit and vegetable intake, the continuous variable is our independent variable, and we move it in to the independent variable window. Before I add the second independent variable age, I'd like to show you what information we received from a simple linear regression analysis, repeating some features from the previous one, but showing some additional functions. Now, this time we go to statistics and we select confidence interval for the slopes as we did before that. I would also like you to select descriptives and collinearity diagnostics. With this, we click on OK and we run the test by clicking OK. As in the previous session, you get several kind of windows. You get the correlation analysis between all the two variables, BMI and fruit consumptions. Here we get the model summary where we had the R square test. In this case, our R square, we can use the adjusted or the unadjusted. Let's use the R square test as 0.088, which means that about 8.8% of the variance or the changes in BMI is explained by fruit and vegetable intake. We get a second number as well, which is the ANOVA test, where we get the F value. The model is significant as it's smaller than 0.05. Our F value is 5.56. Why do I pay so much attention on the F value and on the R square value? Well, the R square value tells us how complete a model is. If you add more variables in the model, more independent variable, the R square gets bigger. If the variable we add significantly improves the model, the R square improves a bigger amount than if the variable is not significant to the model. So you also know in that case that the more variable in the model we have, the bigger the R square. So the more complete the model is. However, the R square doesn't tell you how efficient the model is. For efficiency, we have to look at the F value. The bigger the F value, the more efficient a model is. So if you add a new variable, we definitely increase the completeness of the model as the R square goes up, but sometimes we do not improve or increase the F value. Sometimes the F value even becomes smaller, which means the model is not that efficient explaining our outcome variable. You will also see that this means that sometimes the most complete model is not the most efficient model. So how can you choose which model to use? Well, you have to construct several models with different variables and then to see compare the R-square and the F value. Then you have to make a selection according to completeness or efficiency of the model, which results to present, which is your favorite model. Ideally, you will try to maximize R-square and getting the F value as high as possible. When you scroll down, we have two more important windows. First of all, here we have the coefficient window. This is the slope, so it's an inverse relationship. This means that for 1 unit increase in fruit and vegetable consumption, our BMI decreases by minus 0.633. That means actually fruit consumption has a benefit on BMI of our dwarfs. The test is statistically significant, so the slope is statistically significant, and the confidence interval for the slope is for 1 unit increase in fruit and vegetable consumption, we in best case may even decrease BMI by minus 1.17, or in worst case only by minus 0.096. Anyway, fruit and vegetable consumption is inversely associated with BMI. As we chose culinarity diagnostic, we have to keep in mind one very important thing. Culinarity diagnostic tells us whether one or more variables in our model, usually independent variables, are correlated with each other. The problem is that for multiple linear regression, we cannot include variables that are highly correlated with each other. We would have a problem with collinearity. How do we know if you have a problem with collinearity? We can know it checking at the eigenvalues or the condition index. If any of the condition index is bigger than 15, we have a possible problem with collinearity. If the condition index is 30 or more, we definitely have a big problem with collinearity. We can also look at the eigenvalue. If there are several values close to 0, we also have a problem with collinearity. In our study here, in this model, we do not have a problem with collinearity as the value is 4.236, which is far below 15. In case we have problem with collinearity, this means we have to exclude one of the variables from the model. We cannot run the model because we violate some of the assumption. Good. Now let's add a second variable, and we chose the variable h. We'd like to have the results h adjusted. So we go to analyze, we go again to regression, all the way down to linear regression, and we select now our second variable h. This makes our model now multiple linear regression, as we have more than one independent variable in our model. We don't have to change anything in statistics. We still would like to have the confidence interval, the descriptives, the model fit, and the collinearity diagnostics. So we click on continue and we run the analysis. Now we receive again now a window for the correlation analysis of all our variables. It's a 3x3 window basically. We have BMI, fruit and vegetable consumption, and BMI of the dwarfs, and the same on the other side. We can ignore basically that table. So important is we first check our R-square value. The previous R-square value was 0.088. Now it's 0.15, which means a 7% increase. So adding h to the model, we have a more complete model as the R-square value increase. What about the F value? Well, the F value actually decreased. We still have a significant model as the p-value is smaller than 0.05, but it's less efficient than a model that includes only fruit and vegetable intake in order to predict BMI, as the F value is 5.061. It's not a big decrease. The previous one was 5.5, this is 5.06, so it's a small difference. The next window we check are the slopes. We have here, you see the slope for fruit and vegetable consumption changed. For 1 unit increase in fruit and vegetable consumption during the week, we decrease now BMI by 0.526. In our previous model was 0.6 more or less. But still, that, and if you check based on the p-value, it turns out it's actually not statistically significant. However, age of dwarfs remains statistically significant in the model. So adding age, adjusting for age, the statistical model, fruit and vegetable consumption do not continue to be statistically significant. So most likely it was biased by the age of dwarfs. What about culinarity? Is culinarity a problem? Well, we check the culinarity diagnostics and we see that actually none of the condition index is bigger than 15, so no problem with culinarity. The eigenvalues, we have probably one value, the last one, that is pretty close to zero, but there has to be several values close to zero to have a problem. My suggestion is check the condition index in order to decide if we have a problem with culinarity. You may also think, okay, well, we have included now age of the dwarfs. We'd like also to adjust the study for smoking. As smoking is a categorical variable and is dichotomous, we can add it to the model. So what happens if you add smoking to the model? We go to regression, we go to linear, we select now smoking on our window on the left side, and we move it in as an independent variable. Then we have defined already the statistics and our options, not much to do. So we click on OK, and now we receive the same table now, adding one variable more. First of all, what happened to the R square? Well, the R square actually is the same, it's 15.1%, so we really adding smoking did not change anything in the model. But if you go now to the ANOVA test where the F value actually decreased from 5.0 to 3.3. So adding smoking, we remarkably decreased our efficiency of the model. So adding smoking was not a good option in our model. So what about the slopes? Well, fruit and vegetable intake, the slope is 0.518, still statistically not significant. Age of dwarfs is still significant. For an increase in age of dwarfs, we increase the BMI as the slope is positive. Probably not that clinically relevant as the increase is very small. And if you have a look at smoking status, even when the slope is negative, that means from changing to category 1 to category 2, decreases BMI, the slope is not statistically significant. Furthermore, what about culinarity diagnostics? Well, we have now a problem with culinarity, a possible problem as one of the condition index is bigger than 15. In that case, what would you do? Well, the best solution is not adding smoking to the model because of two reasons. It did not really increase the completeness of the model, it decreased the efficiency of the model, and it was not statistically significant in our multiple linear regression model. And as we have a problem with culinarity, there's enough justification to exclude smoking from our statistical model. This is how to do modeling. Ideally, you add one variable at a time or remove one variable at a time to find out what's the best model predicting BMI. I would basically now continue removing smoking from model and adding maybe education or physical activity or any other continuous variable that follows normal distribution, or alternatively, I would probably add a categorical variable dichotomous to see whether adjusted for that variable, my model improves in completeness and efficiency. I hope you're now able and familiar how to run multiple linear regression and how to interpret the findings. I hope you enjoy the exercises and the quiz. Have fun and have a good rest of the day.